Greetings, YouTubers. Welcome to another episode of Eat by Numbers. I've spent a lot of time talking about calorie density. Did a few videos, made a chart, but now I have a confession to make. The term calorie density is technically imprecise. You see, density is a measure of just two factors, weight per unit volume, say grams per liter, for instance, or pounds per gallon. A gallon of water, for example, weighs 8.345 pounds. When calories come along, now we have a third factor. So when you say calorie density, you really need to distinguish which type of calorie density, because there are two. All along, what I've been referring to as simply calorie density should more formally be called calorie density by weight. It's calories per gram. That's what is important when you're trying to get the most food energy for the least amount of weight. But the other main concern is space. Up against the hard volume limit of a bare canister, how much room your food takes up might actually eclipse the importance of how much it weighs. This video is my attempt to address the other way to calculate density in the calories of what you carry, volumetric calorie density. My first thought was to, do as I do. Calculate the volumetric calorie densities of various foodstuffs and make a chart. Well, in order to do that, you need the volume. Well, the volume of irregular shapes is a notoriously tricky problem. So when in need, I always ask myself, what would Archimedes do? That's right, folks, it's time to get some food wet. I used the displaced water method to measure the volume of a variety of foodstuffs taken from the Hiker food chart. Then just divide with the calories to get the volumetric calorie density in calories per milliliter. Add columns for that volume and density, and here's a mini food chart of what you get. The color coding is arbitrary. It's just a way to help visualize the relative amounts of density displayed. And what you can see is a fairly broad range of values. It goes from 8.3 calories per milliliter all the way down to 1.6. Right, so the goal of the inquiry is to help maximize the number of calories you can fit into a defined volume. The first way to do that is through selection. Try to pick foods with higher densities to make the most of your space. That was essentially my approach for calorie density by weight. Make a massive chart calculating the calories per ounce for as many hiker foods as possible so everyone can just read the list and choose appropriately. Well, that was a whole lot of work, but it was doable because I could just go to manufacturers' websites and enter all of that data for hundreds and hundreds of products. Well, nobody provides volume measurements. Not only is it much more time-consuming doing dunk testing, it also requires that I physically possess every product in question. I'd have to buy and submerge well over 1,000 items in order to make a comprehensive direct measurement chart. So before anybody asks, it's just not practically possible for me to do so. But I didn't want to just tease you and leave you, so I set about looking for a pattern in the data that might help serve as a generalized guideline for how to select more compact things to eat. So if you sort our mini chart by the new volumetric density column, you can see that also clustered at the top are most of the highest calorie per ounce ratings. It's the sort of coordinated coincidence that suggests a correlation. In order to better visualize the relationship between the two types of calorie density, I made a scatter plot. That's not weird, right? I mean, the data's already in a spreadsheet. To make a graph, all you got to do is push a couple buttons. Stop looking at me like that. Anyway, for those of you still here, let's look at what we've got. If I pop a trend line in there, it looks even more like there actually is a relationship between weight and bulk in food. As the calories per ounce increase, so do the calories per milliliter. At the top end, you have olive oil, now not just the champ in weight density, but also easily the most compact form of calories you can carry. And way down here at the bottom are a couple of brands of liquid protein supplements. Water doesn't just add weight for no calories, it also takes up space. And for the most part, it's a pretty conforming group. They tend to cluster reasonably near the trend line. Looking at a couple of the outliers, you can see that the highest calorie nut butters stand out as particularly compact. And below the line, we find things like these Power Crunch bars. They rate ultralight on the food chart, but they're coming in noticeably below trend here because of their airy structure. It's essentially a dipped wafer cookie, the inside of which is filled with empty pockets, giving it the nice crispy texture, but also wasting a certain amount of space. Something else caught my eye. I noticed that peanut butter M&Ms are noticeably below trend, but they're essentially just peanut butter and chocolate, both of which are noticeably above trend. So what gives? Well, I imagine that an individual M would be up where it seems it should be. The issue isn't with the substance's inherent density. The problem arises when these individual units are considered in the aggregate. Put simply, it's a stacking problem. With any coarse particulate, your overall density will suffer from the wasted space of gaps between the pieces. I think that's why these M&Ms are under instead of over. Now, they say a theory is only as good as its predictive power. If you were to hypothesize that the larger the particle, the more the wasted space, well, evidence suggests you might be onto something. Look at where the large chunks of an otherwise very light granola land in comparison to their group voluminousness, or these big butterscotch-flavored survival tabs. This introduces what turns out to be a crucial concept in overall volumetric calorie density: stackability. You see, it doesn't stop with how well candy pieces stack within their little package. The problem scales to include how well all these larger particles stack within this package. And remember our theory of coarse particulates? The stack effect actually has the potential to be more controlling of your overall calories per milliliter than the solid densities of your separate foodstuffs. Over at Far Out Guides, they ran a fun experiment to see how many Snicker bars would fit inside a bear canister. They also tried ramen packages and Mountain House meals, but sticking with the Snicker bars for now. They were able to fit 143 Snickers in a BV 500. That's a lot, but just one more and it would have been a gross amount of candy bars. Anyway, that gave them 35,750 calories in a 10.8 liter volume. Well, look what happened. They show an individual Snickers at 4.3 calories per milliliter. But if you do the math, the density within the canister as packed works out to only 3.3 calories per milliliter. That's the loss of a full point, or a 23% reduction in density due to the stacking effect. It takes a bar that by itself is significantly above trend and renders the aggregate into something that is just below average. For ramen, it's even worse. They start out at a low 1.5 calories per milliliter. The weave of the noodles isn't that tight, so there's a lot of wasted space. And the packages are larger, so the stacking is worse still. Those 80 calories in the canister equate to a functional 0.82 calories per milliliter, which is an even bigger 45% drop in density than with the Snickers bars. In a separate article, they do the math on the theoretical maximum calories you can fit inside a BV 500. You know, just in case you wanted to turn your bear canister into a giant jug of olive oil or the king of all peanut butter jars. So depending on the items, stacking inefficiencies can cut the volumetric calorie density of your food almost in half. And while it's good to know that the lighter foods also trend towards being more compact as individual items, how well those bars and bags packed together looks like it could be even more influential in your overall density. Look again at the list of theoretical maximum calorie capacities from Far Out Guides. In particular, the Jif creamy peanut butter versus good old sugar. The calories per milliliter are strikingly similar, and the theoretical max calories are almost the same. It's less than a 600 calorie difference out of over 60,000 total calories, a difference of less than 1%. Next, look at the calories per ounce of both. It's a 165 versus a 106. That goes from ultralight to heavy on our scale, and it's a 56% increase in caloric density by weight, when the volumetric density is nearly the same. So what's the significance? If you were to fill this canister with peanut butter, just scoop it in all the way to the top, you'd have almost 70,000 calories that weighs 11.9 pounds. If you did the same thing with sugar, it would weigh 18.4 pounds. That's a 6.5 pound difference for almost the same amount of energy. Now check out the numbers for peanut M&Ms. Not quite peanut butter itself, but their calories per ounce are still significantly higher than sugar. Notice the calories per milliliter, however. These very light candies have less than half the caloric density by volume of the heavy-rated table sugar. And what that does to their theoretical maximum calorie capacities is profound. You can get almost 70,000 calories of sugar in a bear canister, but only a little more than 30,000 calories of these. So this goes back to the relative stacking efficiencies of a coarse particulate in comparison to one that is very, very fine. So what I take away from all this is that even though the more weight-efficient foods do trend toward also being more volumetrically dense when regarded individually, it's the stackability of these items when considered collectively that stands to be the most significant factor in overall space efficiency. Life has a way of making you choose between priorities. Usually I pack for weight. I want the most oomph per ounce, so volume isn't my primary concern because my roll-top pack can just expand to accommodate extra space. But in the specific case of hard volume limits, like where bare canisters are required, the priority might shift from weight to space efficiency. In order to get enough calories in the can to make it through that leg of your hike, you might have to consider a few heavier than normal food options just because they pack tighter. Now, that having been said, I'd issue a word of caution. In previous videos on calorie density, I joked about how by far the lightest way to go is simply drink nothing but olive oil. Well, obviously, there are practical problems with that. In other words, you can take any of these principles too far, and the same goes for chasing after maximal volumetric calorie density. I found a neat article on Outdoor Research's blog that serves as something of a cautionary tale to make the point. The author describes his efforts to cram as many calories as possible into a Bear Vault 500 in order to make it through the John Muir Trail. He manages to achieve 32,560 calories, and in my searches, that's the highest number of reported calories I could find for any actual meal plan, not just a can full of candy bars. So how did he get the winning number, and what were the results? Well, as you can see, there's a big jar of peanut butter and some high-density bars, but I think the real magic comes from all the fine particulates. As we've seen, even heavy sugar will give you significantly more calories in a specific volume than some much higher weight density foods. For volumetric density, powders are where it's at. So not only do fine particulates pack more efficiently, internally speaking, but they can also stack more efficiently package to package if placed in highly conformable containers. And if you think about it, only a portion of your items need to be conformable in order to achieve a high level of stacking efficiency. If it's all peanut butter, you lose a lot of that inevitable space between the jars. But mix your jars with baggies, and you can effectively smoosh additional calories into otherwise unusable empty spaces. Just remember not to go too far in chasing these principles. Mr. Shaw goes on to detail his menu for breakfast, which is essentially a blend of fine particulates that even he describes as gruel. He also itemizes lunch, dinner, and dessert. What's interesting are the post-hike notes. Mr. Shaw confesses, while extremely efficient and calorically dense, that breakfast gruel was exactly that, gruel, by which he means to say it was tough to eat. In fact, he adds that large active dudes had trouble finishing it. If he had it to do over, the author would advise more variety, most probably at the expense of some of that density. So, like I said, an amazing effort to achieve record calories in a bear canister, but one that admittedly went too far. I've tried to stress throughout my previous videos that calorie density is only one aspect of a food's performance. Nutrition is another very important factor. Well, so is palatability. Okay, one more quick topic before we get to actually stuffing a can with some food. Going back to our mini chart of volumetric calorie density, as I was doing the dunk tests, I noticed that a lot of the food packages seem to be filled with an excess amount of air. I assume the manufacturers do this to insert some protection for the product inside so it isn't completely smashed or broken into bits by the time you want to eat it. But for our purposes, that's an unwelcome amount of wasted space. And I didn't do it for all the items, but for those that were noticeably padded, I did 2 dunk tests. One with the package in its original condition, and a second measurement after piercing the package with a pin to let the air out. And I resealed it with a tiny bit of tape to preserve shelf life and limit the scent profile. Depending on the puffiness of the package in question, I found that you could save anywhere from 0.2 to as much as 1.3 calories per milliliter. That's enough to move this picky bar from here all the way up here. While practicing packing my own BV500, I discovered that similar gains in volumetric density can be had by replacing stiff pouches with more conformable baggies. And as discussed in the freeze-dried meals video, there are non-trivial weight savings to be had as well. I basically went from about 5.5 days worth of food in a can to a full 7 just by breaking down the packaging. The worst offenders in packaging conformability are these heavy mylar pouches. But things like this granola bag can also trap a significant amount of space in the stiff wrinkles that form when you're cramming it into tight spaces. As long as you do your best to get the excess air out, this arrangement has the potential to yield higher density in your final packing. Okay, so let's pack a bear can. For this part, if you're wondering how I picked what I packed, I recommend watching the video on planning an ultralight backpacking menu for optimal nutrition. It combines considerations of calorie density by weight with all the criteria of optimal trail nutrition and recovery detailed in the Performance Nutrition for Backpackers series. And all of that data plus menu planning tools can be found with the Hiker Food Chart 2.0. Links to the entire food series and downloadable versions of the chart are in the description box below. As far as what went into this baby, I pointedly did not attempt to just go for the biggest number at the expense of all other considerations. I'm not interested in the extra stuff if it ends up being inedible gruel or inferior fuel for the hike. So what you see here is a collection of highly curated calories chosen for their lightweight and nutritional performance. Now, how much of that can we squeeze into a Bear Vault 500? I'll do the unpack without cutting so you can see that everything does indeed fit inside. And calories are calories, of course. You can definitely eat trail snacks for breakfast or cereal for dinner. If you want, you could simply throw in a haphazard bunch of baggies, bars, and jars, and then just eat whatever you feel like in the moment. That would make the distinction between one day's food and another's fairly arbitrary. But because of the way I structure my menus for macronutrient ratios and recovery, I build my menus using defined meals within defined days. So what you're seeing here is a 7-day loadout with extra calories because I had additional space. The format for an individual day looks like this. And this is what that looks like in person with just a couple of exceptions. The daily breakfast portion of granola is half the bag. And for the chocolate, it is just half of this bar. I had room for 4, which is actually 8 portions of each on a 7-day build. That's some of the extra calories I mentioned earlier. As you can see, I aim for around 3,500 calories a day, and I'm averaging over 160 calories per ounce, which rates ultralight on my calorie density scale. For reference, here are the keys of all the color coding shown. See the Performance Nutrition videos for a full explanation. Everything all together charts out like this. I got 25,820 calories, and not as much as Mr. Shaw, but even he admitted it wasn't worth it. And he never mentioned weight. If you're interested in maintaining an ultralight setup that still manages to follow the precepts of performance nutrition for backpackers, this is how it packs. My 3,500 calories a day for 7 days equals 24,500. The extra 1,320 calories in the can serves as one extra breakfast plus a trail snack. And I like that for the possibility that something might go wrong. If I have to stay an extra night on the trail for some reason, it's nice to have breakfast the following morning and a little something for the trail. Who wants to hike out on an empty stomach? Also, if you've ever met somebody in the backcountry that's run low on food, it's good to be able to help out without having to seriously deprive yourself. And again, calories are calories. They can be distributed across any number of days that suits you personally. If you are satisfied with 3,000 calories a day, this layout will feed you for almost 9 days, especially if you don't need dinner on the last night because you'll be in town. In order to maintain the nutritional structure while dividing between more days, you might want to do something like cut down the size of dinner and add additional recovery snacks, but you get the idea. Oh, and 2 quick procedural points about carrying bear canisters where required. Check with the rangers to make sure it's true in your area, but generally the requirement to keep food inside the can is really only for overnight. It's not while you're just hiking down the trail. And that means you can usually carry your entire first day's food outside the can. So for my fully loaded canister that holds 7 days worth, I can actually hit the trail with 8 days of food as long as I consume everything that won't fit inside before going to sleep that first night. And then lastly, make sure to have just a little bit of room for your toothpaste, soap, and whatever else might smell tasty to a bear. And with that, it's summary time. For individual food items, it's good to know that as a general rule, volumetric calorie density increases as the calorie density by weight goes up. In other words, your ultralight favorites are likely to be the more compact options as well. Notable exceptions include anything with an obviously airy structure like wafer cookies or things like pasta and ramen with hollow spaces inside. Perhaps of even greater importance than individual item density is the collective compactness of everything packed together and the problem of stacking efficiency. So opt for fine particulates over coarse. Also, repackage stiff containers with softer, more compliant ones. Conformability allows packages to fill odd gaps to remove wasted space between items. Think powders and pastes. And don't forget to puncture or repack anything that looks to contain excess air. And lastly, remember that you'll have to eat this stuff. Hiking is fun, but it can also be a time of heavy exertion, environmental stress, and unusual wear and tear on your body. So I think of food as fuel first and cargo second. Its performance as fuel and recovery is more important than its weight or volume. But that being said, the purpose of optimization is to get the best mix of the considered criteria. The goal is a loadout of highly effective food energy for the least weight and smallest pack size possible. Hopefully this will help a little bit with that. As always, I very much appreciate your time, and thanks for watching.